Okay, so I would like to thank the organizers for arranging this master's class and also inviting me here to give this series of talks. The goal of my lectures is to define what is an algebraic stack. So I just want to I just want to explain a definition and also motivate why algebraic stacks are useful. So let me start with the category of topological spaces. So this is the category of topological spaces. So objects are topological spaces and morphisms between two topological spaces are continuous maps. So I look at say Rn. So this is the n-dimensional Euclidean space. Let me just call this V. And I'm interested in studying the parameter space for say k-dimensional subspaces of V. So the goal is to construct a parameter space for k-dimensional subspaces of V. So k is an integer. Of course, if k is greater than n, then this is empty. What I mean by parameter space is a topological space. So let me also give a notation for this parameter space or parameter space. Let me call this GKV. So everybody, maybe most of you know this is the Grassmannian, but let me just say what parameter space. By parameter space I mean a topological space whose points are naturally in bijection with subspaces of V. But this is a bit ill-defined. So it's not very well-defined problem, because what do you mean by naturally in bijection? I could choose any topological space. So it just tells you what the underlying set is. It does not tell you the topology. So points of this GKV, they are in bijection. They are just the set of subspaces k-dimensional subspaces of V. So by points, you can think of points as maps from. So these are maps from so let me write this as the set of all homomorphisms or maps from star to GKV. Okay, so star is the topological space which just has one point, and there's just one possible topology on this. So this is it. So when I say points of a topological space, are in natural bijection with maps from the topological space star to GKV. So but as I said, just saying what maps from this to GKV is not enough. So there are many possible answers. So maybe we should look at points from maps from other topological spaces to GKV. So here is a definition. So suppose T and X are topological spaces then a T point of X is just a map from a continuous map from T to X. So a morphism in this category of topological spaces. That is what a T point is. So now I have the notion of not just a point but a T valued point for different possible T's. So in order to actually pinpoint what exactly this parameter space should be, I have to tell you what must T valued points of X correspond to. So sorry, not X now, GKV. So so now let me make this problem more well defined. So T valued points, so of GKV, this parameter space that I am looking for, they must be in natural bijection with families of k dimensional subspaces parameterized by T. So now T valued point means a continuous map from T to GKV, which means for every point of T I have a k dimensional subspace of V. So I have a family. But what is a family? So I need to define what is a family. So so this by this I mean just sub bundles of T cross V. So subsets W of T cross V such that for every point, so W to T, such that for every point of T the fiber is a k dimensional subspace. So this is what I define to be a family. So so given any topological space, so given any X, we get a functor. So we get a functor, we have a functor from topological spaces. So it's a contravariant functor from the category of topological spaces to the category of sets, which sends T to the set of T valued points of X. So it's just the functor home dash X. This is a contravariant functor. So now when I'm looking for this parameter space, I first have the objects that I want to parameterize. I define the notion of what it means to be a family of objects over a given base, and this is actually a contravariant functor. So if I look at, so we have, so here I have constructed one more contravariant functor from the category of topological spaces to sets. Let me call it script G. So this is to every T it assigns the set of families of k dimensional subspaces parameterized by T. So this is a functor because if I have a map from T to T prime to T, let's say, and I have a family of k dimensional subspaces parameterized by T, I can pull back the family and get a family parameterized by T prime, right? I hope this is clear. So a family here just means a W sitting inside T cross V. I just take the fiber product and I get, let's say this is F upper star W sitting inside the pullback of this. Pullback of this means fiber product of this is just T prime cross V. Okay, so I get a family over T prime. So this is actually this actually defines a contravariant functor, and the question we are posing is that is G, is the functor G the functor of points so I'll just define what this is. Is G the functor of points of of some object in this category of topological spaces. What I mean by functor of points is this. So given any topological space, this functor home dash x, so this is called the functor of points. So yeah, this functor, this is called the functor of points defined by x. Let's say just so now I've given you a functor, and I'm asking, is there a topological space whose functor of points is this given functor? So now this is a very well defined problem. So in other words, so now it's clear what do I mean by parameter space. I have some type of objects, I want to parameterize them. I also tell you what families of objects are, which also has the information of how to pull back families. So it defines a contravariant functor, and I ask whether this contravariant functor is the functor of points of some object in this category, and that object, if it exists, I will denote it by GKV. So in this case, it so happens that such an object exists. So so GKV exists. So there is actually a topological space whose functor of points is k-dimensional subspaces family is this functor G, script G. So this also has, this is the Grassmannian of k-dimensional subspaces of V. So I think almost all of you have seen this space before. But I could try a similar problem. Let's say I want to parameterize now, instead of k-dimensional subspaces of V, I just want to parameterize k-dimensional vector spaces. So now we would like to parameterize k-dimensional subspaces. Sorry, not k-dimensional subspaces, k-dimensional vector spaces. So you might think, what is a big deal about this? There is just one k-dimensional subspace up to isomorphism. So the parameter space is a point. But if I try to define what is families of k-dimensional vector spaces, so let me define this functor. So now let's say I denote it by script B from the category of topological spaces to sets. So this is, so B of T, or maybe I can put a K here, so just to say I'm looking at k-dimensional vector spaces. So B, this functor, so Bk of any topological space T, this is just k-dimensional vector spaces. So families of k-dimensional vector spaces parameterized by T. But so I have to define what a family means. So I can just say it's T cross some k-dimensional vector space. In this case, if this is my notion of a family, then this functor is also a functor of points of some topological space, and so everything works fine. But now I could define the notion of a family to be a vector. So this I can just define it to be vector bundles on T. Okay, so a vector bundle is a space. So this is a space E together with a map to T, such that fibers are k I should say rank k vector bundles on T. So this is a topological space E together with a map to T such that fibers are k dimensional vector spaces plus some additional conditions are satisfied, local triviality, and so the so this is my notion of a family. So now this also defines a contravariant functor, but there is one more thing that I have to do. As such, this is not a set. Huh?
You mean isomorphism?
Yeah, that is exactly the point. Yeah. So see, all rank k vector bundles on T, this is not even a set. This is too big to be a set. So I have to say up to isomorphism. So I am identifying two rank k vector bundles if they are isomorphic. So what is the notion of isomorphism? Let's say E and E prime, these are two vector bundles over T. I say they are isomorphic if there is a homeomorphism from E to E prime, so that restricted to fibers, it's a linear map. So I have to go modulo this isomorphisms. Note that in the previous problem there was no need to identify any two objects. So it's already a set, and I'm just looking at subspaces. I don't need to say that when two subspaces are equal, or so here we have to identify in order to make this into a set. Okay, so now it's easy to see that now I can ask whether this Bk is functor of points of Bk a functor of points of some topological space. In other words, can I construct a parameter space for k dimensional vector spaces in this sense? So and it's easy to see that Bk cannot be the functor of points of any topological space. Why is that? Because suppose it were a functor of points of some topological space, and what are points of Bk? So points of Bk, so if not, then points of this topological space, which I also denote by Bk, so points of let's say Bk will be in correspondence to maps from this singleton topological space to Bk, which is just families of vector bundles on a singleton topological space, singleton, and any two k dimensional vector bundles on a point, they are isomorphic. So therefore there is just one point of Bk. So this is just a singleton set. So if this functor is representable, then it has to be representable by this singleton set. But then it would mean that for given any other topological space, so but then given any other T, there is a unique map, so home T and this singleton space. So this contains just one element, so the cardinality is just 1, which means there must be just one vector bundle up to isomorphism on any topological space, which is not true. So therefore this functor cannot be functor of points of any topological space. There is one more question you can ask, that suppose I am given a contravariant functor, then and suppose it is functor of points of some topological space, then is that topological space unique up to a unique isomorphism? So this is true. So let me recall the statement of unidal lemma. So it says the following. So suppose C is any category, and I look at two objects A and B in my category. Then the set of natural transformations, so between these two functors, home dash A, so the functor of points defined by A, to home dash B, so I have these two functors. I look at the set of natural transformations from this functor to this functor. This is in bijection with home AB. So actually it says slightly more. In general, the collection of natural transformations between two functors may not be a set. So this says that it is a set and it is equal to this home AB. So note that if I have, so note that there is a natural map in this from this set to this set. So let me call this phi. So if I have a morphism from A to B, so let's say F is a morphism from A to B, I get a natural transformation from this functor to this functor. How? Because what is a natural transformation? So given any so given any T in this category C, I define a map from home TA to home TB, which sends a morphism from T to A to that morphism followed by F. So G goes to F composed with G. So this is a map, and this is a natural transformation. So which means if I have a morphism from T to T prime, the square that I can write down will commute. So so this tells us that so therefore if I am given a functor, so therefore if I am given a functor, so let me actually make a definition before making this statement. So a moduli problem, so a moduli problem now in the category of topological spaces, so is a contravariant functor, so let me call it M, from it's a contravariant functor from the category of topological spaces to sets. So I can work, instead of topological spaces, I could work with the category of manifolds or schemes. So the idea is that this contravariant functor comes from something, so we will mostly be looking at problems which come from something like this. So we want to parameterize some class of objects, and we define what does it mean by families of those objects, and that is what will give this contravariant functor. And a fine moduli space, let me call this script M, or maybe bold M. So a fine moduli space for this moduli problem is an object M okay, so is is an object M in this category together with natural equivalence of functors. So I have this bold M, so this is functor, so this is isomorphic, this is equivalent to the functor of points defined by M. Okay, so this is what I mean by fine moduli space for this moduli problem. So we have seen two examples, one in which the moduli problem has a fine moduli space, the other example in which the moduli problem does not have a fine moduli space. So okay, so now I would like to first let me make a remark that if there is a moduli space, so for example let me take the example of script G. So this is the moduli problem, so this is the problem where I wanted to parameterize k dimensional subspaces of V. So in this case, we know that there is a fine moduli space. So sorry, GKV. So there is a fine moduli space. So now I look at the identity map from GKV to itself. So let GKV let us consider the identity map. But any map from a topological space to GKV is corresponds to giving a family of k dimensional subspaces on this topological space, right? So this gives this identity map gives a family of k dimensional subspaces, so W over GKV. So this sits inside GKV cross V. So I have a family, and this is called the universal family. So this is the universal family, by which I mean given any other T and a family, let's say W prime on T, there is a unique map from T to GKV such that this W prime is isomorphic to pullback of W. So okay, so I will not write this down. So given any other family on any other topological space, there is a unique map from T to GKV such that this W prime is pullback of isomorphic to the pullback of W. Okay, this is what it means that the functor script G is equivalent to is naturally equivalent to the functor of points of this GKV. So we have so not only we have a parameter space, which means not only we have a space whose points correspond to k dimensional subspaces, we also have a universal family over this parameter space where the point which corresponds to subspace, let's say W, actually has that as the fiber of this universal family. Okay, now I want to give one reason why this functor is not the this moduli problem does not have a fine moduli space, while this moduli problem has a fine moduli space. So let me make a statement and then I will explain it. So so first statement I want to make is home dash x for any x in the category of topological spaces, home dash x is a sheaf. So I am going to explain this. So any functor of points is a sheaf. which will see what it means in a minute. And therefore, if I have a functor which is not a sheaf, it cannot be a functor of points of any topological space. So this is one simple reason why this functor of points cannot be why this moduli problem cannot have a fine moduli space. So let me recall what it means. What is a sheaf? So we want to see what is the notion of a sheaf on a category. So first I'll recall what is a sheaf on a